But even though all my points are irrational, by just simply solving for one of the variables, it's actually not that complicated. So let me take something of this form. Okay, if everything I'm going to show you would be fine if I reverse the order of subtraction, and it has nothing to do with the size of the A and the B. The size of the A and the B will determine the shape of the hyperbola, you know, how squished or how stretched out, but the direction of opening is simply the order of subtraction. I would like to solve for y. So the first thing I would do is I'd rewrite this as y squared over b squared equals x squared over a squared minus 1. Agree? Okay, just a little flip-flop. I would also like to factor out, I'd like to factor out the x squared over a squared part. Which seems kind of strange, but what would that leave me with?
A squared over x squared.
That would just be a squared over x squared? Okay. Now let's multiply both sides by b squared. So far, so good. Let's take the square root of both sides. But y can be positive or negative, so I have to consider the plus or minus thing. Agreed? If I don't consider the plus or minus thing, I can get in a little bit of trouble. Okay, let me press this. This and this are exactly the same. Okay? As x gets bigger and bigger and bigger, just pick a number for a. Heck, a could be 1. It doesn't matter. A could be 2. A could be 3, 4, 5. As x gets bigger and bigger and bigger, a squared over x squared is quickly approaching what? 0. Does everyone see this is a transient term? Which means that this quantity is asymptotic to what? That quantity. So I've got, I don't know, x squared over 4 minus y squared over 9 equals 1. I'm centered at the origin. All right. Well, what do I know? I know that if y is 0, x is going to be plus or minus 2. Do you all agree? So I have 2, 0, and negative 2, 0 are on this graph. Those are my vertices, basically. I'm saying this, if I did plus or minus 3 over 2 times x, well, let's see, 3 over 2, 1, 2, 3, 1, 2, 3. Here's my hyperbola, and I defy you to come up with one more accurately using the supercomputer at UCSD. It will look exactly the same, but it'll take you an hour to figure out how to enter it. This is how you all learned to do it in high school, but you didn't know why, W-H-Y. But you also didn't know why. I'm showing you the reason that you did this. All hyperbolas have 2 oblique or slant asymptotes. The hyperbola quickly approaches that shape very, very quickly. In high school, you were told to just draw 2 dotted lines and then fill it in, right? Everybody did that. And you go, okay, great. But you didn't know why you were doing that. I just showed you. Any horizontally opening hyperbola is asymptotic to this. Why? Because that's the transient term after I solve for y. If you just think putting numbers in, pick a small number for a. A is 1. By the time I get to an x value of 10, my calculator is literally spitting my input out. Whatever I input as x is what it's spitting back out again, times b over a. But the plus or minus is because I was taking the square root of y squared. That's why there's 2. The slopes of these two asymptotes are 3/2 and -3/2. What's the most important part of my hyperbola? It's the asymptotes. The asymptotes determine the shape of the hyperbola, but the asymptotes come directly from these constants. Remember I said the constants don't determine the direction. The subtraction does. The constants determine the shape. Okay? But don't the constants also determine the shape in the ellipse? They also determine the direction of opening because addition's commutative, so it's not the order that I did them in. Right? We just write x squared first generally, but I could reverse the order. So the hyperbola, the most important thing is for me to generate the asymptotes. And then once I do that, so can I work backwards and now you tell me what the foci are? In fact, can you tell me the foci on this hyperbola? Yes, you can. Because what's the relationship in this case between the A, B, and the C? In this case. Kind of a more traditional Pythagorean relationship. C is the asymptote, or excuse me, the hypotenuse. How do I know? Because didn't I just call c squared minus a squared equal to b squared? So that's why it's a squared plus b squared is c squared. Oh, okay. So in this particular problem right here, won't c squared equal 4 plus 9? I don't have to do a whole lot of work in this one, do I? So c is root 13. C is always a positive number. You don't put a plus or minus on C, because then if you did that, you'd have more points. Now what? What's that coordinate? That's root 13 comma 0, and what's this coordinate?
Negative root 13.
Negative root 13 comma 0, and root 13 is a little bigger than 2, isn't it? Is there really anything else to say on this? Not really. So the next thing to do is, okay, let's move the center. I don't know, where do you want to move it to? What point? What's our favorite point to move it to? What do we do with the ellipse and the parabola? Come on. Go back an hour. Where do I want to move the center?
H,
How about HK? Yeah. Let's move it to HK. All hyperbolas are going to be in one of these two forms. If they're traditional hyperbolas. Next day we're going to look at the worst problem of all. We're going to do what are called rotation of axes. Those aren't much fun. But that's a special case. So what I would do in each case, I'd locate the center. Why? Because the asymptotes must pass through the center. That's why it's critical that I get the center right. The slopes of my asymptotes, well, what is the definition of slope? Remember? If I'm using x and y as my axes, the definition of slope is what? No? Neither one of those are numbers. No, the definition of slope is, think calculus, you took a limit of these.
The derivative.
No, slope.
Yeah,
Change of y over change of x. Yeah. By the way, I laugh at rise over run because if I ask you to define what that means, there's not one of you that could define run. It wouldn't even be close. That's an archaic term. Run does not refer to running. Run refers to a calendar. Believe it or not. Anybody here ever lived on a big piece of property? Like lived on a ranch or you've been to places like that and you have a fence that's really, really long. We say it runs the length of the property. Is the fence running? No, a movie played for several weeks, and we refer to the run of the movie. That's the horizontal distance on the map of the calendar that started January 1st, ended December 31st, and I wrote it horizontally. The run of something refers to a horizontal expanse that is measured, not a verb of movement. By the way, nobody uses that language anymore. So when people say rise over run, they know what rise is, but the run doesn't make any sense because it's not the same thing. No, the definition of slope is change of y over change of x. Or, if you're not using x and y, change of the vertical over change of the horizontal. So what did you do in calculus? You took a limit as the change of the horizontal approached 0. Does it have to be x and y? No, I just gotta get vertical versus horizontal. Which one measures the vertical change? The one under the y squared. Doesn't matter which one's first. It's still gonna be b over a, isn't it? By the way, get this right. Everybody gets the slope right on this one. People struggle on this one because they change the definition of slope. They literally will change the definition of what slope is. That's dangerous. Don't do that. No, it's vertical change over horizontal change. That's fairly simple. So let me come up with a simple example here. Give me a second to reverse engineer something, okay? So we've got x squared minus 4y squared plus 2x plus 32y minus 27 equals 0. I think this will work. I hope this works. All right, what do I want? I want the center and I want the asymptotes. There's really not a whole lot of other information I need. If I have the asymptotes, then drawing this is trivial. Does it open vertically or horizontally? The correct answer is, I don't know yet. Well, but it's x squared minus y squared. No, you always write it in that form. But I won't know until I get to the end of the problem if it's x squared minus y squared or y squared minus x squared. Oh, because if I just arbitrarily multiply both sides by -1, would that change what it is? No, but then I'm in at y squared minus x squared. That doesn't change what it looks like. So I need to do what we did before, and that is complete the square. All righty. So we've got x squared plus 2x plus blank minus 4y squared plus 32y plus blank equals 27 plus blank plus blank. Okay, some of the pluses might end up being minuses, by the way, right? Okay, so here, this is easy. This will be x plus what squared? What goes here? 1. So what goes here? Different color, obviously. Boom. All right. Here, I need to factor this first. So this would be minus 4 times y squared minus 8y plus something. So this would be minus 4 times y minus, what goes here?
4.
So what goes here? 16. Did I just add 16 to the equation? What did I add? I added negative 64, didn't I? Ooh. Is that important? Yeah, that's kind of huge. Okay, I used black. Because I just added negative 4 times 16 in actuality. Now let's look at the right side. That's pretty obvious, that's a 1. So what do I have on the right side now?
90.
27 plus 1 minus 64. $36? Negative 36. Ooh, I need that to be a positive 1. What's that going to do to my order of subtraction? It's going to switch it, isn't it? Ah, because I have a negative 4 over negative 36. That's going to be y minus 4 squared over 9 minus x plus 1 squared over 36. Aha. So remember, the way I wrote it originally, you always write the x squared first with a positive coefficient. That's just kind of this, I said standard form. But I can't tell you vertical or horizontal until now. Now is it vertical or horizontal? It is vertical. So that means it's going to look like this. No big deal. Okay, so let's now pick it apart and let's find all those little pieces. Don't need that anymore. All right. The center. Four negative 1, right? Negative 1, 4. Oops, we got to pay attention to which variable is first, don't we? Okay. Before I indicate what my asymptotes are, I always like indicating what are my slopes. Plus or minus what? 9 over 36, 36 over 9, either one of those? No, that's a 3 squared, that's a 6 squared. So it's plus or minus what? What numbers are you using? Is it 6 over 3 or is it 3 over 6? 3 over 6, which is plus or minus a half. Okay? Vertical change, horizontal change. Never get that confused. Well, but I wrote it in this order. That doesn't change anything. The number under the y is the vertical change, just like before. Okay, now can you tell me my asymptotes? Yeah, here's the way I would write it. Use your point slope formula and just leave it. So, y minus the y coordinate equals slope times x minus the x coordinate. Would it be okay for me to distribute gather terms and write it that way? Of course. Now if I do that, what would I get? I'd get y equals, let's do the positive, so it'd be 1/2 x plus a half plus 4. If I do the negative, then it'll be minus a half, then plus 4 would be what? Plus 7/2. Now, I want you to graph these two lines. What'll be easier? Graphing these two lines or doing the first one? Doing this one. Because you're just going to go straight to the center and then draw two lines that have a slope half. Yeah, actually leave it like this. This is correct. This is actually not as useful as this. Because from here, can't you tell where my center is? And the slopes? Yeah. So you could leave it like this if you chose. So the most important thing was the asymptotes. Can you also now tell me where the foci are? Because there's really nothing else to say. I'll put that up on top. Well, it's opening vertically, so would it be safe to say that it's going to be -1 comma and -1 comma? Would that be correct? Only the vertical is changing. What is my c squared equal to? What am I doing with these two numbers here? Adding them. By the way, don't tell me that c squared is the square root. That's just bad math. No, c squared is 45. C is the square root. A lot of times we try to go too fast and we say something silly. So 3√5 is a distance that I am moving from the center, but vertically. So this will be, what's my center? 4 plus 3√5, and over here 4 minus 3√5. I've told you the center, the foci, the slopes, and you indicated that it was opening upwards. Could we freehand a pretty accurate graph with essentially no work? Yeah. All you need is the center and the asymptotes. Now, what is useful though? It's useful to, by the way, once I have the asymptotes, that's all I need. But if I wanted to draw, oh, I have the center and the asymptotes, but there's, gotta be careful here. Everything I've said is true, everything I've said is correct. But can I draw an accurate graph yet? So negative 1, 4 is about here. My slopes are plus or minus a half, which is going to be about like, and it's opening vertically. Where does it start? Oh, I still need something else. What do I need? I got to have at least 2 points. Did we draw one over there? I think I erased it. What 2 points do I need?
Okay.
Well, that's not a word, and no, those aren't on the graph. Foci, and no, you don't see the foci, we've already stated them. I don't have any points. I need points. Am I just going to randomly put them somewhere? No. What are the only 2 points we need? What are the only 2 points you actually typically work with? Starts with a V. Vertices. Those are the only 2 points you graph. Those are the only 2 points you know. How do I know the vertices? Because I am moving up and down how many units from the center? How many units from the center am I moving? 3. Nobody wants to take a chance. 3 units. Now I can draw it. If I don't have the vertices, I have no points. It's not random where I'm drawing it. The only points I ever need are the vertices. And those I can read right from the beginning. Those are easy. Those are easy. So if you said, oh, how did you come up with your asymptotes? Well, didn't you say go up 3 and then over 6? I mean, is that how you do slope normally? Oh, yeah. Up 3 over 6, down 3, backwards 6. Okay, that's my slope. That still works. This is hyperbola. So why do we need hyperbolas? They're interesting creatures. They're trickier than the other guys because of the differences. And the derivation was a little uglier, but you know, it was so similar. Let me show you something kind of interesting. This is, it's not critical, life-changing information. Let's suppose I want to contrast and compare almost identical equations. Now, just to make it easier, let's say A is bigger than B for now. Because I said that the graphs are ridiculously different. I mean, there's no way that you could ever see these graphs look similar, but they have so many things in common. So let's say that that's plus or minus B, that's plus or minus A. Okay. So here's my ellipse. Okay, so there's negative A, 0, negative, 0, negative B, 0, B, A, 0. All right. Now I want to do this guy. Well, according to that, if I go up A and over B, I'm about here, I'm about here, I'm about here, I'm about here. I said we're opening horizontally. So the orange is the ellipse, the green is the hyperbola. Did they use a lot of the same information? Yeah. Because the shape was entirely determined by the values of A and B. Directions of openings and things like that were determined by other things, but isn't that kind of crazy? Here's the hyperbola, the ellipse fits perfectly right sort of in there. And they would share the same vertices from that standpoint. Now you're never going to do 2 things simultaneously, but I'm saying here's how you can kind of compare and contrast. Interesting. So, why hyperbolas? Well, there's an example, although they don't refer to it as hyperbolas. There's an example from a movie that I really like. Okay, but I'll give you a simple one. All right, here's Earth. You know, here's us. You know, we're the United States. There's a little thing. I don't know. Now, we have something going on in a couple months. Actually, something starting next month in the same country, you know, where they whack a tennis ball. And then a few months later, there's a big event, and people are going to get together in another place. Everybody know where that place is? It's going to be the most watched event for the last 4 years and the next 4 years until the next 4 years. People come from all over the place. Yeah, where's that going to be?
No idea this time.
Paris.
Paris?
Which is over here somewhere. Okay. So you want to turn on your TV and watch that. Well, a few things have to take place first. A few generations ago, we couldn't do that. So what they do is they send a signal out here to one of these guys flying around called a satellite. And he sends his signal over here to somebody flying around in another satellite. And he sends it here to your house. Because hyperbolas, or technically hyperboloids, the three-dimensional ones, are primarily used for gathering certain types of waves. But not necessarily sound waves. By the way, they could be radio waves. What would you call the TV wave? What would you call those things? I'm not sure we refer to those waves, but microwaves, different waves. They gather waves. Now, the problem is, what you need to see, you need a big hyperboloid. Oh, wait a minute, I have an idea. We can make our own big hyperboloid. We could put it on our roof, let's say, and then we could invite people over to watch the sporting event and charge them money. Heck, sell them food and alcohol and call ourselves a sports house. Oh, wait a minute. No, there are sports bars, aren't there? Oh, shoot. Okay. So maybe I just want to watch it at home and invite my friends over. So I put a hyperbola up on my roof. I still have one, by the way, from DirecTV. They never came and took it back. Kind of drives me crazy. What are we talking about here, folks?
The old dish.
Satellite dish. It's a hyperboloid. Did you know that? But more fun than, okay, this works. Did anyone here see Kingsman?
Yeah.
Love that movie. Do you remember what happens when they destroy his satellite? He calls his buddy, another billionaire, and he says, hey, you know, can you link me up? So they linked him up with his satellite to talk to the other satellite to then beam down the bad waves, making people do bad things. You know, I'll just leave it at that. People did bad things. But it was kind of fun, right? Okay, so these are the hyperboloids, or the hyperbolas are collecting the waves and then transmitting. See, the reason we can't do this directly is called line of sight. Can't get from here to here. That's why we don't necessarily need it, let's say, within our own country, because we're not going around a great landmass in a sense. Are there places where it's difficult to get reception? Are there places in the country? Yeah, because of natural phenomena, geographic, right? You might have a mountain right next to your house, and the mountain has a lot of iron ore in it, or there's things that can affect the waves. But this is one of the simpler ways of thinking about this. Okay, so the waves that are gathered. Now, I have had a hard time finding this article, but I do remember the situation. I remember the article. Most of you weren't alive. In 1990, the Gulf War. How many have heard of the Gulf War? In 1990, Saddam Hussein basically started. He was blowing up the oil wells and different things. Creating fires. They were using people as human shields. They were doing all this stuff. But it was the Scud missiles. They were firing things called Scud missiles at civilians, at American troops. They just went all out. We had very, very little loss of life because it was uncanny. We don't know where they're being launched from, by the way. They're secret hideouts everywhere. They're being launched. We were picking them off in the air. Now, there's not a long time between launch and landing when you're close by. We were picking off the missiles in the air before they did any damage. Because the moment we knew where it was launched, we were able to figure it out. And I remember reading an article, literally said something to the effect of hyperbolas won the war. As soon as they were launched, we were able to see something about the pattern. We put it into our computers. And this is circa 1990, so think about the technology today versus then. Pretty crude technology, right, 34 years ago. But because of that, they were able to quickly determine exactly the flight pattern, and they were knocking them off in the air. And that war ended really, really quickly, like I said, with very minimal loss of life. because of our ability to do this. And I remember reading this article and bringing it to class, like, see, this is why you learn about hyperbolas. Well, no, but the fact is it was hyperbolic stuff that was going on in terms of the flights and the trajectories, but actually it was the waves. I don't know if it was sound waves that was created or exactly what that they were using, putting in the computer, but it was so cool because it's the mathematics that allowed us to do this. Without that, we wouldn't have been able to do this. We wouldn't have been able to know where they were coming from. Just because there's a missile in the air, if you don't know its exact trajectory, right? First of all, you don't know where it's going to land, and you certainly can't fight it because you don't know exactly where it's going to be every moment. But the ability to do that was pretty incredible. So, for our practical purposes, hyperbolas are not as useful on an everyday thing like parabolas were, for example. But the three-dimensional hyperbolas, I'm going to give you just a little bit of an insight. Because this is what you're going to do in Calc 3. And part of the reason you need to understand some things about hyperbolas is because the three-dimensional versions of them are very cool. There is only one thing in Calc 3 that you will find truly evil, and it involves hyperbolas. Now, you thought cosecant and cotangent were bad. Yeah, they're bad, but only for limits. If I took a three-dimensional shape, now I'm going to give you a simple example. Okay, let me start with something like this. Because I'm giving you the analogy because you have to understand there's a three-dimensional version of everything you do in 2D. If I wanted to consider the graph of this, okay? True? The derivative of 0 at x equals 0? That means I have a horizontal tangent at x equals 0. So, when I'm drawing this graph, it basically looks like this. Do I have a maximum at the origin? Do I have a minimum at the origin? Do I have neither at the origin?
Neither.
Yeah, remember, to be a maximum, it has to be the highest in an open interval. To be a minimum, it's got to be the lowest in an open interval, and it's neither one. No open interval is it ever the highest or the lowest. That's because this is one of those rare times that you have an inflection point where you have a horizontal tangent. And that we call this a confounding kind of situation. So here's the thing. Earlier today, Gail and I we had some time, so we climbed Everest, right? We had a little bit of extra time. So we climbed Everest, right? She's a little faster than me. And there was a complete whiteout. You couldn't see 2 feet in front of your face. So she was way, way, way ahead of me. So she's already gotten to the top. So I'm climbing Everest, and I get to this point, and I say, finally, I've reached the top. As she's descending, she gets to this point and says, finally, I've reached the bottom. Because you can't see very far. Are either one of us correct? No, it's neither the top nor the bottom. It's just a horizontal tangent. Like I said, this one confounds us because shouldn't I get a max or min because the first derivative is 0? No, that's the only place I can get a max or min. It turns out I don't. There's a three-dimensional version of this, and it's evil. And it's so much fun. Let's face it, come on, the evil characters in the movies. I'm a big Star Wars guy, but Luke Skywalker, really? He seems like the most boring person ever. You like Darth Vader, right? You like all the bad guys are so much more fun. So much cool. Okay, so this is called a hyperbolic paraboloid. What does it look like to you if I drew this well?
Horse.
Looks like a horse?
Camel.
Looks like a saddle.
Saddle, there we go.
I don't know that I'd call that a horse. Okay, this is called a hyperbolic paraboloid. This is the most confounding thing we look at in 3 dimensions because we find maxes and mins in 3D, right? If I have that, upwards opening paraboloid, it's going to have a minimum, right? There are things that are actually not that complicated. Now, from the inside, this is what I see. So, I'm looking at this thing head on. If you've ever ridden a horse, right? Clearly, that's the low point, isn't it? You're looking straight at it. That's the low point. Now, you're standing to the side. So now you're looking face on the horse or you're behind the horse. It might be easier to look behind the horse. Now, when you're looking behind the horse, you see all these downwards things. So this is clearly the highest point, right? Because it's a downwards opening parabola right there. My parabolas are going like this. So when I'm standing behind the horse and looking, that's clearly a peak, isn't it? So when I'm standing behind or in front of the horse staring at this thing, or imagine that the horse is made of glass. The horse is transparent. That might make it easier for you to see this. Okay, the horse isn't in the way. When I'm looking at it from this point of view, it's clearly a maximum, but when I'm looking at it this way, it's clearly a minimum. So which one is it? Which one is it? Well, both is not an option, therefore what's
Neither.
probably neither. It's probably neither. So we have a really, you'd never figure out this name in a million years. We have a name for this. This is one of the most important points we study in Calc 3. It's called a saddle point. Saddle points are truly evil and confounding, and they cause all sorts of problems, which is why they're so much fun to study, because they come up a lot. So I'm doing everything right, and I'm trying to figure out if I have a maximum or minimum or something. It turns out I have a saddle point, so it's a neither. But it'll show up in much the same way this point showed up in 2 dimensions. They're not the same thing, but there's a lot of similarities, okay? So that's one of the reasons we study hyperbolas, is because we have to understand the 3-dimensional versions of them, because they do come up. Circles, spheres, those are easy to translate. That's not really hard. Paraboloids from parabolas, those are really not hard. Heck, eggs from ellipses, those are really not that hard. That guy causes all sorts of issues, okay? All right, just go and stop. All right.